Hi, I'm Suhani Sharma, a current senior at the Westminster Schools, and this is my project for using AI to help diagnose bipolar 1 disorder. Alright, we're now just starting the presentation of navigating bipolar disorder and possibly leveraging AI for early detection and diagnosis. So we'll go over a brief intro about the history and what we really looked at in the beginning for this project. So bipolar disorder. Bipolar disorder is a unique illness categorized by its severe mood-altering symptoms that result in diagnoses that are often conflated with other similar disorders of highs, which pertains to mania, and of lows, which pertains to depression. So it's been identified in people ever since the ancient Greco period when it was first described by Hippocrates, and throughout history it was constantly classified as manic depression due to its 2-week-long periods of severe depressive and manic episodes. In the 1900s, more work was done for identifying psychiatric disorders, including bipolar disorders, and finally, in the 1950s, Carl Leonhardt introduced the concept of polarity in diagnosis. So the problem we're tackling today is the problem of misdiagnosis, and bipolar patients exhibit both symptoms of mania and depression to various degrees, which means they've been a subject of a number of misdiagnoses. And this has been seen in many studies, but today we'll just be talking about 2 studies finding that 40% of bipolar patients are often first misdiagnosed with depressive disorder. These studies were taking place in 1999 and 2000. The study found that antidepressants were often overused for the treatment of bipolar disorder and how bipolar disorder continues to be misdiagnosed, with common misdiagnoses including depression, schizophrenia, and other anxiety disorders. Misdiagnosis is prevalent, with depression often being the most common misdiagnosis. Patients with bipolar disorder are misdiagnosed for a mean time of 5.7 years, but another study found the average time to also be 7.5 years. Misdiagnoses result in a longer diagnosing time, more hospitalizations, and a higher rate of hospitalization for patients. With all of this in mind, we begin to question where the lines between diagnoses of select 3 disorders, bipolar 1, persistent depressive disorder, and manic syndrome, blurs, and how well doctors and researchers can evaluate these discrepancies, especially through the utilization of a novel language parsing technology found in LLMs. Next, we'll be going through just the methods and how we chose the test that we chose. So for PHQ-9, we use that to screen for depression, the reason being that it has excellent internal reliability and retest reliability. Correlation between the PHQ-9 completed by the patient in the clinic and what the mental health professional said was 84%. Along with this, the PHQ-9 was brief but also accurate, with it being unlikely that any other depression measure would be as or more accurate. Then for bipolar disorder, we chose the General Behavioral Inventory, or 7-up, 7-down inventory. So for this, we chose the sensitivity of approximately 75, which is the ability to correctly diagnose those who have bipolar diagnosis, and specificity of above 97%. So that's the ability to diagnose those who do not currently have a bipolar diagnosis. There are many different versions of the test, but we chose the 7-up, 7-down version due to the short amount of questions, making it easier for the user to take. Then for mania, we chose the Altman Self-Rating Mania Scale. So while we acknowledge that there are limitations in the assessment of mania outside of what's commonly self-testable, we've chosen to utilize the Altman Self-Rating Mania Scale. So that's a 5-item scale, which assesses mood, self-confidence, sleep disturbance, speech, and activity level over the past week. We chose it because of its strong combination of both sensitivity and specificity at 85 and 86%. Along with this, it's been found to be fairly accurate when comparing to SADS, which has baseline diagnoses. As it stands, we've opted to utilize these 3 tests, but in the future, we hope that with enough training in our model and purveying of the results, we allow the model to utilize its language recognition to select a relevant test, perhaps spanning across multiple disorders. Next, we're going to be going over large language modules. Okay, so just a brief definition. Artificial intelligence, or AI, is the overarching field encompassing machines capable of stimulating human intelligence. So as you can see in the picture to the right, the large circle is AI, which is the overall field. Then we have machine learning, which is ML, and that's a subset of AI where systems learn from data and improve their performance on a specific task without explicit programming. So as you can see in the diagram, machine learning is a circle that's also in there. And then you have deep learning, which is part of machine learning, which is a more advanced form of ML employing artificial neural networks with multiple layers to analyze complex patterns in data. Along with this, you have generative content, which is AI models capable of creating new original content such as text, images, or music. And we often see this with ChatGPT, which is a prime example in our day and age of generative AI. And then, so for the diagrams on the right, we see just a general overview of how this is structured, with artificial intelligence being a larger circle that kind of describes every part of this. And then we have the more specific examples of ChatGPT, which is both an artificial intelligence and machine learning component. Okay, so now how does LLM work? So it starts off with an input text. For example, you have the sentence, the cat sat on the. Then you have the tokenizer, where it identifies each individual word as a token. So for example, you have the word the, then cat, then sat, then on, then the. Then you have embedding, where each token is converted into a numerical vector that represents its meaning and relationship with other words. So as you can see in the diagram, you have the word cat that actually becomes a number and it relates it to the other words in the sentence. Then you have the encoder, which processes the sequence of embeddings, capturing the context and relationships between the words. It creates a numerical representation of the entire sentence. So this is really coding the words into numbers. And then you have the decoder, which is the opposite. This part starts generating the output text word by word. It takes the encoder's representation and the previously generated words as your input to predict the next word. So now you have text generation, which is the decoder has already generated the cat sat on the, and now it predicts the next word. So based on the patterns it's learned in the past, it'll suggest other words such as mat, chair, or floor, and then the model samples this from the probability distribution. And in this case, let's just say it chooses mat. Then you finally get your output text where you have the full sentence. So the cat sat on the mat. All right, obviously, next we're talking about HIPAA because that's a crucial part to understanding the psychiatric field. So, de identification is crucial for safeguarding patient privacy. By removing all personally identifiable information, healthcare organizations can utilize data for analysis and AI applications without compromising patient integrity. Offline servers enhance data security by preventing the transmission of sensitive information over the internet. So, this is really using the Wi Fi to make sure that it's impossible for data to be transmitted, and this reduces the risk of data breaches and unauthorized access. So maintaining HIPAA compliance is paramount. Obviously, offline servers help organizations adhere to HIPAA regulations by keeping protected health information within a controlled environment. Utilizing both de-identification and offline servers empowers healthcare organizations to leverage the power of AI while upholding these high standards of patient data privacy and security. Now we're going to be going over some ways to train the LLM. So we have multiple ways, but starting off, we're going to start off with pre-training. And this involves training a language module on a large corpus of text data to predict the next token for a sequence. So we've already established what tokens are in the last two slides, and it's been done in a self-supervised manner, meaning that the labels for training are generated automatically from the input data. Then you have fine-tuning. So after pre-training, the model's weights can be further adjusted or, as the name implies, fine-tuned on a smaller data set or a specific task to adapt it to a particular context or improve its performance on the specific task. Typically, this involves adjusting the weights of the last few layers of the model while keeping the rest fixed. Then you have reward learning from human feedback. This approach aims to adapt the model's behavior to align more closely with the human expectations or need. It involves providing the model with additional labeling effort, often in the form of human feedback or rewards to guide its learning process. Then you have prompting, which refers to providing specific instruction or query to the language model to generate desired responses. It doesn't directly alter the model's internal representation, but guides the output. Then we have RAG, which is Retrieval Augmented Generation, and this represents a hybrid approach that combines pre-training with retrieval-based techniques, allowing it to generate text by synthesizing information from both pre-trained language modules and external knowledge sources. So in our project, we use RAG for the doctor to look back on past data and see cases that were similar to the ones that's being currently described by the patient. Okay, now we're going over data and results. This video doesn't include the video of me actually showing the model, but I've also linked that video, so feel free to watch that after this. So here's the general flow of how AI works. The user enters a psychiatrist's story on the input, so you can see the tiny picture to the right where that's really the interface of how it looks. Then after the user sends the psychiatrist story, it sends it to multiple LLMs, for example, ChatGPT, Llama 3, and then you get common test names that it recommends. The user is then able to pick a test, and then the call agent is called to run the appropriate test. The user then answers the questions one by one after being prompted by the AI, and then it returns the results, how they scored on the test. Okay, now going over future possibilities. So there's a future possibility of switching tests because in theory, if we wanted the user to switch tests, if they were failing the bipolar test, then we could do that with further models. We would initially give all the depression questions or all the mania questions at once, and let's say they were failing all the mania questions, but got all the depression questions to be high, then we would switch them to a respective test for depression, being PHQ-9. The same applies to mania. In order to tell whether the user should take PHQ-9 or the ASRM during bipolar disorder assessment, we did a self-sort through the bipolar questions to tell which questions correlate to depression or mania. By using the 7-up, 7-down inventory test, it was easy to identify 7 questions that indicate mania and 7 questions that indicate depression. So we self-sorted through the questions that were hinting at mania and depression, but we were able to do it by looking at the language used in the question. And if we find that the user had answered very often or almost always to all the mania questions, we direct them to the ASRM test. Sorry. This applies to depression with the PHQ-9 test. It's not the current model, however, but with future work, we'll establish this as well. Next, going on to phase 2. So when we have the user entering the psychiatrist story as the input, it'll check the database with similar stories. So this will be future work that we're currently working on, and we need more data to actually look at past similar stories. So when the psychiatrist story is inputted and you check the database for similar stories, if you find similar stories, then they will suggest a test based on previous patient cases. If not, it'll do what it did in the past, where it sends the story to multiple LLMs such as ChatGPT, Llama 3, and gets common test names that they recommend. Then the user picks a test, it calls the agent to run the appropriate test, and the user answers the questions one by one because it's prompted. Then it returns the results, and after, this is different, it'll add the user story to the database for future reference to continue back to the loop of finding similar stories or not. Then we have phase 3, where the user enters the psychiatrist story as input. You check the database, see if you find similar stories, yes or no. Yes, you suggest a test based on previous stories. No, you check multiple LLMs. User picks a test. You have your call agent. User selects questions, returns results, and then it'll add the user story to the database again. But this time, it'll fine-tune the model based on the doctor's input and what they decide, and the model guides between different tests. All right, that's it for the brief overview of really how this project works and the basic understanding of AI and using it to diagnose bipolar disorder. Thank you for watching.